Thank you all for being here. My name is Anand Venugopal from the Stream Analytics team at Impetus. I have with me my colleague Saurabh Datta, who's a product manager, and I lead the business for the Stream Analytics team. We're presenting a case study from a large financial services institution that we did with replacing an old technology stack with a Spark-based system for real-time credit card application approval. So it's not the transaction approval, it's really an application approval for credit cards, right? So that's the case. We'll take questions at the end, and in some cases, to protect the confidentiality of the case, we're abstracting some details and just showing some samples. But we'll be going into the use case itself as well as the implementation. So as I said, the business background of the use case, the existing system and challenges, and followed by the implementation, what we did. So the customer is a large financial institution with 50 plus countries, 50 plus million credit cards. They get about 4 million applications a year. Now that comes down to about 10 or 11 applications every minute. But the depth of the analytics and machine learning that needs to happen does consume scale. So the simple objective of this of the institution obviously is to acquire legitimate, responsible, trustworthy customers. And every decision point is really 3 decisions. One is yes or no, and the credit limit and the APR, right? And it's a sub-second response. It's a sub-second response time that's needed to make a decision. Although it seems easy, there was challenges there. So the use case is simply that you and I go to the credit card website or respond to an email, click through the application, fill up the form, the logic gets executed, and the decision is communicated. And in case where there is a decision that's unable to be made, then it just gets moved into a semi-automated manual process. So the core logic is, of course, estimating risk, estimating the debt repayment risk, really, and to limit credit risk of the lender, and obviously for the financial well-being of the customer so that we don't over-leverage ourselves in spending too much on the credit card. The risk scoring factors are obviously predictable, but there are quite a few. Credit history, credit usage, loans that you're already having, other credit cards. As I said, it's all fairly obvious: job type, income band, debt ratio, which is the current leverage of debt versus the income level, and credit scores. All of this goes into a model for all the decisions. So the first, let me go into the decision flow itself on how these factors are used and how the models that are used lay out. So it's a combination of both internal and external data that gets used in this decision. The decision flow is when the request comes in, there's a callback from the credit bureaus, the callback from people like Axiom to get consumer demographic data, and there's a share of wallet data as well that comes from internal sources in the bank. So all of these 3 external sources of information get pulled. There's a lot of enrichment and data derivation that happens on these data points that become inputs to the model itself. And the models, as you can see, is a whole array of models based on the customer segment in terms of geography as well as the demographic segment. There's actually a number of models. It could go from 10 to as many as 100 that gets chosen for this particular application that comes in. So once there's a yes or no decision that takes place based on the model score, the model actually puts out a 0 to 1 score, followed by the decision of yes or no. The decision is based on policy of the bank at any given time, followed by the credit line decision, which is the amount, followed by the price at which the customer gets the credit, which is the APR. And so that's the overall decision flow. The models that actually are used for each of these 3 decisions are different. So the approved decline is based on a decision tree, and there are obviously numerous instances of the decision tree model. Followed by the line and credit limit is actually given by a regression model, and all of these are all supervised models based on the data in the bank already on successful customer base. And finally, the price and APR uses 2 models. It's the nearest neighbor as well as k-means clustering. In this case, we're showcasing the k-means clustering model. So the decision tree itself is where it starts. It's typically a binary tree to increase the speed of execution. The entire decision, for example, in this case, it's like salary less than 50,000, other loans, yes, debt ratio. The entire progression of the decision actually happens as a binary tree, so for speed of execution, that ends up with a 0 to 1 score, as I mentioned. And that score is obviously then taken by the policy to say yes or no. And in the case of yes, then there are 2 more decisions to make, which is first credit line. And for credit line, as you can see, it's basically linear regression. And we train the model based on existing data, correlate with existing successful customers, and then say, look, based on this, for this particular model score, this is the limit that we provide based on the learning of the model. Similarly, again, for APR, it's based on clustering. As you can see, there's a basic pictorial illustration here. Based on the demographics of the incoming customer, as well as all of the details of the case, for existing customer bases, for existing customers, if there is matching this profile, so you basically get matched to the existing set of clusters in the bank, and that's how your APR gets chosen. And in the case of nearest neighbor, again, this is cluster center versus the distance from the cluster. In the case of nearest neighbor, it's like literally a computation of how many nearest neighbors you're close to. So that would be the overall decisions that be taken in this model, and we'll talk about the implementation next. So the existing system in the bank used Microsoft Stack, C#, Microsoft SQL Server. Nothing wrong with the stack itself, but it's essentially an old generation traditional system where everything was on a single box. So it really wasn't scalable. The flexibility was very limited. And because of the nature of the business itself, there's a lot of changes coming through in terms of models, models being continuously improved and needing to be deployed again and again. And policy and rules as well what needed to be changed. So overall, the changeability, change management was very, very cumbersome. And there was an accuracy limitation because of the scale. So if a model just gets 3 months of data, there's a certain amount of accuracy it can get. But if you train the same model on a year of data, the accuracy is obviously much greater. So that was another big objective for the new system. And there was also an isolation in terms of silos for the data scientists working in an environment where they had, of course, Python and other tools, just moving models across from the development environment to the operational environment. And every time there was a change in terms of moving, changing, updating, that was, again, one of the issues that they wanted to solve. And really bringing in a collaborative, unified environment for execution and management of all of the models. So all of these became objectives for the new system, and there were a few more, such as self-service, ease of use. They wanted to really, were kind of dreaming of and asking for a self-service system which would be a scale-out architecture, and then also to reduce the latency of the decision itself. They were taking more than 3 to 4 seconds. They really wanted to get to a sub-second level of performance at scale. So the other big thing, and this is the last bullet, which is the data lineage and audit capability. So obviously, many of us know now that in a regulated environment, people are expected to go find a particular application and find out exactly what happened to that application and where that application was blocked, approved, or denied, and why. And that kind of lineage and audit capability was also missing, and that became another goal for the new system. So these were all of the objectives going into the new implementation, which we did with the Spark-based stack, and Saurabh will take us through the rest.
Thank you,
Saurabh.
So as we can see that we fairly had a decent list of goals to take care of. And when we looked at these goals, Spark became a natural choice, especially because of the different libraries it provides. So it had Spark Streaming and Spark ML, which we have extensively used. We have used Kafka to read the data from the source. Then we are using HDFS for storage. And similarly, all the lineage data was pushed into HBase. So these were the core technologies that we chose. And to develop this, we used a visual platform that we have. It's called Streamatics. So It's not that you can't do it in Spark, but it's just that with the visual tool, we really had very tight deadlines, and when we used this, we were really able to achieve the goals really fast. So again, Spark streaming gave us the capability of writing streaming jobs very easily. And since it is an extension over Spark's core API, all the advantages of Spark core automatically get inherited. So when we build the platform, it's automatically scalable. It could respond to high throughput, and the platform that we build is automatically fault tolerant as well. So what happens is, as we get the data, Spark automatically divides the data into smaller chunks and then apply transformation over this data. In our case, we were not looking at a high throughput based application. Our application was all about low latency. So we really had to play a lot with what kind of data and what kind of batch sizes we have to put so that we get a very low latency application. Similarly, our choice for Spark ML was also obvious because it really, all the models that you build, they are automatically parallel. You could run it in a distributed environment. So it consists of all different kinds of algorithms. So out of the 4 listed algorithms here, we are actually using 3. We are using classification, regression, and clustering as well. We did not use collaborative filtering because these are the set of algorithms which are primarily used for recommendation systems. Spark ML also provided us a set of utilities. For example, for feature selection, feature transformation, if you have to really make your model efficient, you could do hyperparameter tuning, and once your tuned parameters are in, you could do model evaluation, and it also provided us a set of different statistical functions as well. So with all this in mind, we had all the tool set that were needed to design a proper system which could go in production. So I'll just walk you through the training architecture. So this looks pretty simple. So all of the algorithms that we used were supervised. So we had all the label data with us. We stored it in HDFS. We read it through Spark, and then we handed over this data to Spark ML. So once the model got trained, we put this model into a model repository which was built in HDFS. So you read data and you process, and again you store it in HDFS. So the storage system which was used end to end was based on HDFS. This is typical to any other training pipeline that you would design. But then we again used a visual tool to achieve end-to-end objectives. As I said, the steps remain the same whether you use a visual tool or you actually hand code everything. The steps remain the same. So we read data from HDFS, and then we applied certain data validation checks. So before you hand over data to a model, there needs a lot of data preparation steps. So for example, when we are training the data, due to some human error or something, the label itself might be missing. So there are certain key attributes in the data which you cannot miss at all. So these kind of things need to be checked by applying data validation checks. And similarly, by any chance, if you have given any invalid characters. So we really wanted to filter all this stuff out. So for that, we have applied certain data quality checks. And the next step, again, is an important one wherein we are eliminating an outlier. So when you have training data set, it is based on actual data which has been previously used for scoring. So what usually happens is there are certain exceptions in real life. So in this example, even where the score of a particular applicant was low, still the card was approved. So in certain cases, you really want to filter out this data from your model's input. Otherwise, what will happen is the model you create, that will itself be faulty and it will be skewed. So any other data point that is coming in real time, it might predict give you wrong results. So you really want to get rid of all these outliers out here. There were certain attributes which were, again, not very important from the model's input point, but they were still needed. So here so for example, as you see, in this example, I have taken age for the data to be imputed. So certain fields which are missing, you may want to actually populate them. There are a number of ways of imputing data. The first one is the most easiest one, is you just replace it with a constant value. That's the most dumbest way of doing it. The second way could be you could apply a statistical function like mean, median, or you could see what's the most frequent value occurring in the age. So you apply a certain statistical function and then you replace the value. But the most smart way of doing this is you apply a model-based imputation. So what will happen is this kind of data itself will be an input to a model, your model that gets trained, and then you use that model to predict the value of age or any other missing data that you have, and then you replace the value. So once your data gets prepared, then comes the step of actually feeding that data into the model. So here you will do things like feature selection. So if you have like 100 attributes, out of those only 10, 15, 20 attributes are important. Either you could choose all the features manually, or Spark also provides certain algorithms out of the box which you could use and do a feature selection. You could do then transformation. So the model itself needs either a vector or a decimal kind of value. So if you have a text value, you may have to transform it into a vector before it goes as an input to the model. The model gets you select the model. So Spark, as I earlier mentioned, has an array of different models based on your requirement. In this case, we are training the decision tree. So you choose the model and then you specify various hyperparameter values. So you specify a range, you play along a bit and see which is the best model which is coming out. So as you provide different values of hyperparameters, multiple instances of the model training gets executed, and based on the parameter you have provided. In this example, since we are training a tree, we really need to tune the max depth and max bin type of parameters as hyperparameter tuning for the tree. And then the method of evaluation I've chosen is RMSE. So I really want to optimize this value, the value that I'm seeing here, 1927. So the RMSE stands for root mean square error. So I really want to minimize the errors over here. So again, as I said, Spark has all the model evaluation algorithms which comes built in with it. So you just choose the algorithm and automatically it will tell you which is the best model. Once you have the model, you can just store it in HDFS and use it for scoring from there. Here is our reference architecture for scoring of the data. So as the user fills in the form, the data lands on Kafka, and then we pick it up using Spark streaming. That's where we make call to external third parties, internal banks repositories, and once data is enriched, we invoke ML models then. So the model provides us an output which is then pushed to Kafka and also gets stored in HDFS. So this could be referred in future. So you have the entire end-to-end scoring piece. This is deployed over Yarn, and for auditing we are using HBase. So for this as well, we have used the same visual UI. So we are reading data from Kafka, and then external web service calls are made. So all the credit bureaus and data providers, they have REST service in some form or the other, which you could just call and get the response, and then you actually enrich your incoming record with these third-party calls. The bank itself maintains certain history of the customers, which help to further enrich the data. Once you have the enriched data, you try to segment the customer, and then based on the segment he belongs to, a particular tree model gets executed. As you can see, there are a number of tree models being trained over here and used. So based on the customer segment, a particular tree model was executed. The tree model essentially gave us a score, and based on the score, we were able to take a decision whether to approve the record, reject a record, or in certain cases, we keep the status in pending, ask for more information from the customer, and then actually go back and either approve or disapprove the card. So based on the decision that's taken, there are 3 forks that are being created over here, and based on whatever decision we get, a particular fork is then evaluated. If the card is approved, in that case, the line and the price model executed. So as a result, we get all the 3 values, whether the card is approved, what kind of credit limits we want to provide, and at the same time, at what APR we want to provide the card to. So all these decisions are taken step by step. Now, there was another crucial requirement which was around auditing. So as a record lands in, what was the exact path that record took to finally get to the destination? Here, if you see, as the data landed on Kafka, there were all the external calls being made. So whatever you see in green is the path that the data point took. So here you see that all the third-party calls were made, and then the topmost decision tree model got executed. And because the card was approved, the center one or the approved flow got executed. So that's how you could go back and see. I know the font size is a bit smaller, but it also shows the amount of time that each node used to spend. Each node spent to execute the process. So you could actually go back and see, is there any chances of optimization over here? This was kind of a deployment diagram wherein we had several clusters dedicated around a functionality. So for the transport, for all the data transport thing, we had a particular cluster for Kafka. Similarly, we had a compute cluster on which a dedicated 5-node Spark cluster was used. Similarly, there was a dedicated cluster for storage, and the BI tools were again deployed on a dedicated cluster. And especially the Spark and HDFS part, this was again orchestrated by Streamatics. This was just a 2-node installation based out of using a sticky session and load balancer. So let me give you some details around the project. So again, as I said, we really had a very small amount of time to understand the problem and to even execute it. So we executed this in Q4 of 2017, fairly recently. We took like 3 months to achieve this end-to-end with a team size of 4-member team, and we had a data scientist as well. This was built on Apache Spark 2.1, and this was an on-premise deployment for the bank using Hadoop on Yarn. I would also like to lastly share some of the key learnings. Some of these might look obvious, but this is just a recap, and it's important that you keep these things in mind. Because you are interacting with a lot of different discrete systems, what happens sometimes is the data format is not consistent. In our system, we are using JSON as a standard data format to interact, but the credit bureaus were returning us XML data. So we decided to convert that XML data into JSON once, so that every time we do a join or correlation, there is no impact on the performance. So once and for all, we converted into JSON, and then we applied all the transformation. Similarly, since we are doing a lot of calls to third-party APIs, it was important that we add timeouts to it. Otherwise, what will happen is your pipeline will just keep on waiting for the response, and you will not get it. So you don't want to do that. You may want to just apply timeouts, and if you do not get a timeout in the stipulated amount of time, you may just want to do a timeout and fail the record. You also need to optimize the stragglers. So what happens here is in a particular stage, if a particular task is taking a lot of time, you could just see it on the Spark UI, see which is the task which is taking most of the time, go back and optimize that particular piece of code. So make sure you do that. Otherwise, the task that takes the most amount of time is going to drag your pipeline to a lot of extent. Avoid excessive logging. Sometimes what happens is whenever you log, you might go back and write into a disk based on how you have designed it. If possible, avoid excessive logging. Again, if you have a long-running pipeline, try to use checkpointing. And as I said, on the model side, make sure that you are taking out all the outliers. This could be, again, as I said, done in 3 ways. The best way to remove outliers is you use models to do that. Spark has an array of different algorithms for hyperparameter tuning and metric evaluation. Feel free, you should use that, use metric evaluation as much as possible so that you get the best model as an output. And when you are training really large trees or ensembles, make sure you enable use node ID cache. So what happens is when you enable this, your the trees that you train or the ensembles that you train, they train really fast. This is kind of an optimization. So make sure you take care of these things, and I think you should be able to achieve what you want to. So with this, I would like to conclude, and Anand, if you could just do a quick recap.
Yeah, sure. So on a recap for the goals, ease of use for stakeholders was obviously a big item there. And as you saw, I think the assistance of a visual tool for building and debugging and deploying and managing this application turned out to be a major accelerator for us. And that took care of the ease of use for stakeholders. So they continue to use it and build it, and it's an extensible tool. That's the visual platform called Stream Analytics. For scale, again, the achievement of being able to train models on much larger data sets was accomplished by training 1 year of data versus 3 months of data, just because of the parallelism and performance that Spark afforded us. And so that dramatically increased the ability to train much more accurately for all the 3 models that we talked about. And the latency was reduced to sub-second, around a second, from 3 to 4 seconds from the previous system. So that was a sufficient accomplishment for this particular use case. And given, of course, it's Spark streaming in the current generation of it, you really can't do much more smaller latencies than that. But this satisfied the use case for this particular scenario. And as a unified collaborative platform, there was also a lot of need for a unified visual environment where you could do model testing, A/B testing, champion challenger, especially in the development side. So this visual framework actually gave us the ability to fork data into multiple models and actually do model training and scoring with multiple models at the same time, doing evaluation of the accuracy and performance of various models so that you can actually literally swap and test different models. The data lineage and audit capability also could actually be turned on and off on the system. The screen that you saw before was an example of that screen, so you could literally just step through the whole flow, and that achieved the data lineage and audit capability. And we actually use HBase to store the lineage data as well. We've had questions about whether that is a runtime issue. Does it impact performance? There is an overhead. But that's why you can turn it on and off. So you could run the first few days with on, and then you can turn it off when things are stable, etc. So that is really the way in which we accomplished all the objectives of this use case. And so that concludes the presentation. So we'll open for questions at this time. Thank you. Yeah. Saurabh, you want to come? There's a question in the back over there on the left side.
Hi, so I have 2 questions. So one is regarding the latency. You said 1 second latency, right?
Yeah.
And that was including the API calls to the external third parties?
Yes.
Okay.
Yes. So as I said, we had put a timeout of 200 milliseconds. So if we do not get a response within 200 milliseconds, we would actually fail that record. And there is this entire orchestrator layer which keeps a track, whenever it pushes the data into Kafka, it keeps a track using a TTL, whether it got the response in that stipulated 1 second or 1.2 seconds at max. If it does not get a response, it will also fail the record.
Okay. The second question, the models themselves, did you instantiate the models in your Spark streaming app, or was that running a separate microservice that you were accessing using some REST API?
Can you come again? Sorry.
So the ML models that you created, right? The decision trees and all that stuff. Did you create instance of those models in your Spark streaming app, or you were running those models as a separate microservice that you access using some REST API?
No, so at this point it's just a Spark streaming app, but yeah, definitely we are trying to get it into a microservice and host it in some kind of a microservice-based environment. Yep. That's
so the models were instantiated within the app, which means every time the model changes, you have to restart the app, I guess?
No, so what happens is, there is, to an extent, yes, but what happens is, there is a separate batch pipeline which runs and it updates the same model on the same path on HDFS. So, okay. Yeah, so that path remains the same.
Okay. So you're reading the model from HDFS every time you need to score?
No, so it comes in memory and there is this listener which is there. So every time there is a change in the path, it will automatically inform the system that there is a change.
I see. Okay. Thank you.
All right.
Thank you.
So for the credit line model that you use, are you training separate models for each of the segments in the decision phase, or is it just one model for all the segments in the credit line?
So for line, it is just one model.
Yeah, two questions as well. Regarding the labels, are these credit default labels, or are you really learning decisions from historic data? Your approve reject, are those based on previous approve reject decisions?
Yes.
Or, okay.
Yes.
So are you learning the approve reject decisions from the previous system or only from the manual review?
No, so basically what happens is the previous system do its prediction, and later on someone actually manually looks at that.
Okay.
Yeah, and so there is a manual process which comes in picture.
Okay, so all of your labels are from some level of manual review.
Yes.
Okay, and the second question is regarding your population segmentation. Is there any reason why you decided to do that manually as opposed to increasing the depth of your tree and letting the tree figure it out, what the best split is?
No, so what happens is, based on the geographical location, so there might be a different decision tree model just for the US, and similarly there could be a different set of model for Canada, and similarly one for Europe. So based on the geography, there is a different decision tree model, and every model is a little bit different from each other. So that's
largely driven by bank policy. So it's
okay. Yeah, okay, so it's more, I guess it's more policy, because I'm either that or you actually observed that having geography as a feature and then letting the decision tree decide what the best split is. So in this case, you're kind of forced to have a different model per geography.
Exactly.
Okay.
Yeah.
Do we have any more questions?
how often do we retrain? Once a week in this environment.
Can you talk about how much time?
Which was again not possible earlier. It was very hard to do that. Go ahead.
Can you talk about how much time did you spend on the data quality and refining that out of the 3 months?
Exactly. So, we had to give this deliver this in 3 months. So we had a specific, data scientist who was looking into this part. So while the development team was working on creating the pipeline, we used certain dummy models to actually create this. And while the data scientist, he kept on working on this, and within the period of 3 months, we were able to deliver end-to-end.
And there was also a lot of accumulated intelligence from the previous case. So on the data quality, right? They knew the problems. They wanted a system to implement it. So again, there was a whole bunch of rules that they wanted to implement, which we quickly got into the system.
So this was not built from scratch. There was an already existing system there.
Yes. We have an elaborate set of data quality operators as part of this tool, which is typically an issue, right? So thereby we are going to be demonstrating this platform tomorrow in another talk at I think 11:20 or so.
Okay, thank you guys.
Thank you.
Time is up.
You.
You can continue with further question and answer right outside. Thank you.